Homomorphic function encryption, hot or not? Imagine wanting to eat some chicken feet at your Union house. You don't want to get awkward looks and you're too lazy to get up. You decide to get some first year to season it for you without them knowing what it is or what they're doing to it. How can you do this? The answer is to surround the chicken with a magic opaque container containing the spices. They shake the box, seasoning the chicken feet, but they don't know what they're doing or what they're doing it on. Now further imagine that you're a computer. The chicken feed is your private data. The first year is some computer in the cloud that you want to offload some computation on, and the seasoning process is some encrypted function. This is homomorphic encryption. Currently, schemes for both public and private key systems have been made. And since this presentation is only 10 minutes and there's quite a bit of hefty background math, I'm going to give a very broad strokes view. Anyone who wants to understand those bits properly should read my paper or some related ones. The first question is, what should a homomorphic encryption scheme have? It should be semantically secure. Example of this is if you give it a function that retrieves the item at array position 3, if the scheme encrypts values with the same value, then the cloud computer can just look at the encrypted values and go, that value got sent, and it will have some idea of what the function does and what values are stored. So you want your homomorphic encryption scheme to encrypt the same value with different values. The ciphertext should not scale as the function is done. This keeps you from getting a huge ciphertext. It should be computationally viable to use the scheme on modern day computers. You want to be able to send your own encrypted private key. This is to use in a process called bootstrapping. And you want it to work in a post-quantum world. It's easiest to understand the types of homomorphic functions in terms of logic gates. Partially homomorphic functions like one sort of gate. A good example of this is unpadded RSA, which is multiplication, or paleo, which allows addition. Some homomorphic functions allow both, and you can make any circuit using AND or gates, which are the equivalent of multiplication and addition, but a limited subset of circuits at a limited depth. And fully homomorphic encryption allows for arbitrary circuits of arbitrary depth. This is the holy grail of homomorphic encryption. The backbone of a semi-homomorphic encryption scheme is a function that the user can use to generate private and public keys, a function for the user to encrypt data, a function for the user to decrypt data, and a function for the cloud computer that takes the user's public key, the encrypted function that it should perform that's been converted to a circuit, and some number of ciphertexts. The first viable fully homomorphic encryption scheme was proposed by Craig Gentry in 2009. Most of the current fully homomorphic encryption schemes are based on this. The encryption problem he uses is a lattice problem. And the basic process he goes through is he selects a somewhat homomorphic encryption, he squashes the decryption function, and then he just runs his required function, and whenever the noise becomes too large, he runs a bootstrap operation. And his scheme encrypts 1 bit. Squashing refers to when you want to reduce the complexity of a decryption circuit or ciphertext, so the semi-homomorphic encryption scheme can process it as it is limited depth. For example, you might want to change the degree of a function from a quartic to a quadratic. And the security of the scheme is now dependent on the sparse subset sum problem. Most fully homomorphic encryption schemes are dependent on adding noise. However, with too many operations, the noise becomes large enough that the ciphertext is drowned out by it. Some noiseless schemes have been proposed, but no viable ones have yet been developed. This is why Gentry proposed something called bootstrapping. When the noise in a somewhat homomorphic encryption scheme becomes too large, you squash the ciphertext so the somewhat homomorphic encryption scheme can work on it, and then create a circuit which decrypts and then re-encrypts the ciphertext to get a new ciphertext. This removes all the noise from the ciphertext, but retains all of the work that the functions have done on it. To do this, the secret key must be passed to the fully homomorphic encryption scheme, but just an encrypted version. Modern day fully homomorphic and somewhat homomorphic encryption schemes are based around three problems: the approximate great common divisor problem, lattice space problems, and learning with error plus ring learning with error. These are all hard, so they're safe from quantum attacks. This is based around integers. Just to consider all of these integers, you can see the approximate GCD is 100. In this case, the public key would be A and P, and the private key would be Q plus some error term. It's hard to determine Q given A and P. Without noise, this problem is pretty easy to solve. With noise, it's somewhat hard. By somewhat, really big key sizes are needed to maintain security, and experimentally functions took days to evaluate for reasonably secure keys. So people don't really use this much for modern fully homomorphic encryption, so the rating is not hot. A lattice is a grid of points, so they're evenly spaced in n dimensions. With a basis, you can create the whole lattice. This allows for some mathematically hard problems. An example is, if you're given a long basis, as in this diagram, can you find the closest point to the origin? Gentry's original scheme was based on lattices. And for fully homomorphic encryption, fairly large key sizes are needed. Shout out to Eleanor. If you want to learn more, go and watch their presentation. I'd rate this so-so, since the key sizes are still fairly large. So A, B, and E and R are all arrays. E contains terms that are much smaller than A and B, and these terms are all divided by some modulus. R and A is a public key, B and E is a private key, and it's hard to determine B given R and A. This man explains LWE and how it works in homomorphic encryption quite a bit better than I can. Our ring learning with errors is similar to learning with errors, but it uses polynomials. So R equals A times B plus E, where all of these terms are polynomials. E is some error noise term. And yeah, the public key is R and A, the private key is B and E. It's hard to determine B given R and A. All operations are done in a finite field. This is similar to like modular operations, but for polynomials. If it's a cyclotomic polynomial, this reduces to the approximate shortest vector problem, which is a lattice problem, and it's hard. You can expect around log n key sizes compared to learning with errors. So it has the smallest key sizes of all of the problems we've proposed so far. Therefore, I'd rate this the hottest. So why hasn't fully homomorphic encryption been adopted yet? Gentry's scheme was based on encrypting single bits. So nowadays we need to use SIMD and vectors to use this in parallel efficiency. It's both pretty costly and quite hard to implement. Bootstrapping and squashing are usually the most expensive operations by orders of magnitude. A somewhat homomorphic encryption scheme can process a function in a few milliseconds, and the fully homomorphic encryption scheme might take hours to process. Even though the overhead is a polynomial, it's a very large polynomial. Gentry overestimated that to do a Google search with a fully homomorphic encryption scheme would increase running time by about 1 trillion. Memory-wise, it's very inefficient. Some schemes take megabytes to send a single bit. Limited support is offered for a system which might have multiple users if they're operating on the same outsourced cloud computer. Bootstrapping sends the encrypted secret key. Some attacks can recover 1 bit every time the secret key is sent, so there's quite a bit of inherent insecurity. Some things that might make fully homomorphic encryption viable are the discovery of some sort of cryptographic problem that allows for a noiseless, fully homomorphic encryptive scheme, better bootstrapping, so just improvement, and stronger computers to allow the overhead to not be so significant. Somewhat homomorphic encryption has been used in electronic voting, but has not had much commercial use. So I'd rate it not quite hot yet, but it has quite a bit of potential.